This what you see is a 12 volts 55 watts car headlamp bulb. Okay, 12 volts 55 watts H3, and these two are from a 12 volts adapter. Yeah, supply is on. Now this what you see is a pin from soldering iron tip. And guys, this what you see is a power transistor. Okay, you see MJ13009. It's a dead power transistor, not working. Okay, so let's check that first, if it is dead or not. So let's first check if it is dead or not. So guys, the easiest method to check a transistor if it is dead or it's working is by connecting the collector and emitter to the power supply and see if it's a closed circuit or not. Emitter means this one will be connected to the negative of the supply, done, and one terminal to the bulb and this terminal to the bulb. You see, it's lighting up. This indicates that even though I have not given any supply to the collector with the base, which is the basic for starting or powering or switching on the power transistor, it is still turning on, which means it's a short circuit. There is a little delay, but still it's a short circuit. You see, it's lighting up equally well with the base terminal. What about the collector and the base? Okay, it's again short and base again short. So the power transistor is completely dead and short. So let's try and make a soldering iron with it. Now guys, after inserting the soldering iron tip in the hole of the power transistor, we have to find out the maximum resistance terminals. Okay, so let's check the resistance between this and this. It's 21 ohms. Now base and emitter, again 21, and collector and emitter, it is 0.6 ohms. So we have to go for the maximum, either go for collector and base or base and emitter. Now let's cut off this unwanted terminal. And now I'm going to do the temperature check on this soldering iron. Okay, temperature. Yeah, done. Now the temperature should rise. See, it's rising rapidly. Well guys, there was a little change of plan. This was the initial soldering iron that I was making. You see, it was working, but I had to wait really long to get it heated up. So I decided, why not connect it directly? And you see, here you will see that I tested it before. I am going to show to you that the soldering occurred at the tip of the power transistor. So guys, the first part is to extend the wires with these 12 volts clips. Okay, let's keep this one aside. Okay, and this one is base and this one is emitter. So yeah, this one is base. So base is positive and emitter is negative. So I will connect positive to the base. Done. Now emitter. Done. Yeah, and this is done. Red for positive and black for negative. Well guys, here as you can see that I have connected it to a 12 volt 7H UPS battery. Okay, and that's the wires. And that's my soldering iron. You see, in this video, I'm going to make an inverter without a transformer. Now, a few years back, when I completed my BTech in 2014, I had an electronics book in which there was this basic circuit of an inverter in which they used only a high value inductor and a capacitor, and they created switching to create an AC on the output of the circuit. But the only problem is that it is not going to be very powerful, but it is a basic circuit to understand if an inverter can work without a transformer and step it up. So here is the capacitor. This is a 7100 microfarad capacitor with 40 volts DC. It's a DC capacitor. Okay, that's one of it, C1. And this is an inductor. It looks like a transformer, but it is only an inductor. Guys, a transformer has 4 wires, 2 for input and 2 for output, but this has only 2, these 2, which makes it an inductor. Okay, so that's L1. And now the final, the transistor 13009, which is this one. And before proceeding, let's check if this capacitor is working. Okay, so at present it is showing ohms. Let's change it. Diode, resistance, and you see NF, nanofarad. It automatically goes to microfarad. Well, this one is red, so I'm going to go with red being the positive and blue being the negative. So it is showing 8 or around 7 microfarad. Okay, 7 point something, and here as you can see it is 7100 microfarad. So now we can directly start with the connection part. First comes the capacitor that I will stick over here. Done. Then comes the inductor. Okay, done. Now as the circuit shows, one terminal of the capacitor will be connected in series with one terminal of the inductor. So we will do that. One terminal of inductor connected to one terminal of capacitor. Now comes the switching device, which is this. Let's connect this to. Okay, and done. And guys, now comes the transistor wiring and connection. You see this terminal, the first one. Okay, this is base, this is collector, and this is emitter. Okay, so I will use the thinnest possible wire, the very thin wire for the base. Now comes the collector. Let's move it a little away. Yeah, collector is stuck pretty good. And now comes the last one, the emitter. Okay, so the soldering part is done. Now comes the connection part. This wire that you see, it is the collector terminal of this transistor. So this terminal will be connected to the tapping point at which the capacitor and the inductor are connected to each other. Okay, which is this point. So that is done. Okay, now guys, this black terminal that you see, it is the input as well as the output terminal. So let's strip the wire a little to give an extension for the positive supply. So you see here the positive input will be connected. So yeah, now we have the positive and the negative. So guys, first comes the multimeter that we will connect to measure if the voltage is high enough at the output, pointing it towards 750 volts AC. Now I also have to connect a 12 volts DC source to convert it to AC. You see 12 volts, 7 amperes. It's a UPS battery, and truthfully speaking, a really old one. So this red terminal, as I told you, was the negative one, so it will be connected to this negative terminal. Okay, and I have a clip. Yeah, negative has been connected. This is the base wire. This does not need any connection right now. and this is the positive connected to be connected over here. So guys, let's touch this wire and see if it reflects some voltage. As you can see that it does not reflect any voltage because the base wire is open. So we can connect it permanently. It is not going to drain the battery or discharge it. Okay. Now we have this open base terminal. So if we connect it to this capacitor terminal, this one, okay, then there should be some voltage. You see, the voltage is so high, around 550 volts AC. Again 1000 volts, 1100 volts. So you can see that first I'm touching it and then I'm quickly removing it. Touching it and then removing it. And you see some voltage reflected. So this is called the switching circuit, and every inverter has an automatic switching circuit. At present I am doing it with hands, which means manual switching, but for an automatic inverter, automatic switching is needed. So for that I am going to use this simple trick of DC motor switching. Okay, this toy DC motor. So guys, what you have to do is cut off one of the winding wires of the armature of the DC motor. This is going to create the on-off switching process, an automatic on-off switching process, one of the most basic possible switching. And after doing that, install the armature, the case and the brushes back as before and connect one of the terminals of the motor to the base terminal of the transistor, and the other terminal will be connected to the positive terminal of the battery. So this is the other terminal of the DC motor connected, and all I have to do is touch it to this terminal. You see at present it is not showing any voltage. Yeah, done. Now all I have to do is connect a 3 volts battery here, and this should start reflecting a very high voltage. So this is my 3.7 volts lithium ion battery. Okay, so let's start the show. One terminal over here. You see it showed high voltage. Okay guys, now I have glued these two motors on this metal platform. I'm trying it at the second time, and let's see the voltage. So as you saw that the maximum voltage reached was somewhere around 50 volts AC. So guys, this what you see is a mixer motor. It's in a pretty bad condition. You can see that the wiring and the winding has been burned out, at least for the rotor, although the brushes can be reused. So let's open it up without any further delay. Yeah, this looks good, can be put to some good use. Let's keep it aside. And so are these. Now comes the removal of the top head. Done. Again done. Now comes the brush tapping removal. This portion is keeping this strip in its place, so we will have to push it. Okay, once again. Yeah, got it out. And we have a full good condition brush that we can put to good use in some motor. So now we can remove the stator at least. And yeah, here we have a stator which seems like it's fine, but to be sure about it, we will have to put it to resistance check. That's the rotor, pretty bad condition. Yeah, not good at all. Well guys, I just forgot that I also needed this metal base from this, so obviously I will have to remove this cooling fan, and it is jammed pretty good. You see, completely rusted over here, and the legendary WD-40. As you can see that I've removed the fan, and all I have to do is remove this. Yeah, done. Washers. and the armature is now completely separate. So guys, finally it's time to do the resistance check for each of the two poles, and you see that this pole has 3 wires. So we will have to figure out the maximum resistance wires and then leave out the third wire. So first confirming the resistance with the pole with 2 wires. And what we have here is 2.1 ohms. So the resistance is quite low for so many turns. So but still, let's check for the other one. Okay, yeah, you see the resistance for this one is around 4 ohms. What about this? That is 6.3 ohms. What about these two? 3 ohms. So guys, the bad news is that I think there is some shorting in this winding because the pole resistances don't match, so there is going to be imbalance. But guys, I was lucky enough to find an identical core, identical in diameter, but it is much more powerful with thicker copper windings, you see, and it also has these pinouts for easy connection, which was not the case with this cheap one. And this was also lying around and it fits perfectly, so I thought why not use it. You see, this was for this piece, it fits perfectly here, and this piece fits perfectly here. Okay, perfect. And the only difference is the core thickness of 26.2 mm. Okay, 26.2 for that one. Now comes this one. This one is 20 mm. Now guys, this was the armature of that universal motor from a mixer, and I have chipped away these two sides to place the magnets, and I'm going to use the perfect concave magnets. Okay, you see how it fits over here. Yeah, and same for the other one, and it's something like this. Perfect. Well, now it's finally time to assemble all of them together and check how much electricity it can generate. So base comes here. Done. Now goes the field or rotor. Yeah, initially it was armature, but now it is field, or you can say rotor, and then the top head.
Yeah, done.
Yeah. Done. Well guys, here on the shaft you can see that I have placed WD-40 to make it work smooth, and same for the base. There are no brushes, and you can see the magnet. Okay, also the air gap is maintained as very less, so the magnets are going to induce huge EMF on the field poles. So let's measure the voltage generated by one pole. Well, here I've pointed the meter towards AC voltage because it is going to produce AC. You can see simple rotation, and it is generating around 2.5 volts AC. 3.3, yeah, 3.5 volts for one single pole with hand rotation. Imagine guys, when I connect both the poles in series, then obviously the hand rotation voltage is going to go around 7 or 8 volts. And with rope rotation testing and if I run this motor with this drill machine and all, then obviously the voltage will easily reach around 12 volts. And also if you see the thickness of the copper winding, it is good enough to produce good current. So guys, today we are going to do the performance and generation power testing of this modified mixer motor to dynamo. I have added this drill chuck at the back because it was moving up and down a lot, and also it is easier to rotate it like this with this chuck. And now comes the important part. This coil has these two terminals and this coil has these two terminals, and we have to connect both the coils together in series in such a way that the voltage gets doubled when I rotate the shaft with this. Okay, so initially it was generating, in my previous video which you saw, it was generating around 3.5 volts AC. So our target is to achieve around 6.5 to 7 volts with hand rotation. So I have connected one pin over here and the other one I will connect over here. Well, right now I'm doing just hit and try. One terminal connected. Now the terminals that are left out are, one terminal is this and the other one is this. So to this terminal I will add this. Done. So now in total I have two terminals. So to these two terminals I will connect a multimeter and then measure the voltage I am achieving. Now let's rotate the shaft and see if the voltage has increased. You see, the truth is the voltage has decreased. So this means that the connection I have made are just the opposite of what I needed. Okay, so I will have to change that. And now the voltage generated should be higher. You see, the voltage has increased. This means the connection are correct now. Simple rotation and easily 1.5 volts. Let's go a little higher. 6 volts. Whoa. And I think I will be doing the test with this drill machine. Okay, it's easier to do that, but before that let's connect this black tape on this wire. Okay, yeah, okay, see for the voltage over there. Why is it not measuring voltage beyond 7 volts? So 10 volts was the max I could get with this drill machine. Again, yeah, 10.32 volts. Well guys, now I'm going to repeat this very test with a bigger 350 watts drill machine with an even higher RPM and torque. Let's see how much, sorry, it's going to be AC volts. Let's see how much AC voltage it generates. Okay. $22 volts. Around 24 or 23 volts. Pretty good voltage for AC. So guys, now I'm going to connect this car headlamp bulb. Okay, and since it's a DC lamp, so I am using a rectifier, 35 amperes bridge rectifier. Okay, well, there is a lot of lighting in the room. Let's turn it off and then do this test again. Pretty good. Although guys, the AC was not completely purified because I didn't add any additional condenser or capacitor to these two DC terminals to pure the DC line, because of which there was a lot of flickering in its operation. You see, a lot of flickering, which would not be the case if I had connected a capacitor. So let's do that and then check out the results. So guys, this is a 7000 microfarad 40 volts DC capacitor. So I'm going to connect it to this and I hope for better output results. You see, the lighting is much more better. There is very less flickering now. Well guys, now to the output terminal I have connected this 220 volts transformer. So I'm going to boost the voltage from 24 volts. Yeah, it is generating 24 volts to 220 volts, maybe even more. Let's see how much voltage it produces at the output. Connections have completed. Let's turn it on. So as you saw that it is generating pretty good voltage and transforming it then to 256 or 260 volts, which is exactly what we get here in India in our AC sockets. Well guys, this one what you see is my cordless drill battery charger. Okay, see 48 volts, and I'm using this instead of a mobile phone charging demonstration because this one has this LED light indicator and it is two-way, red and green, so I can do good demonstration with it. And this is my 48 volts lithium ion battery pack that this charger is going to charge. Okay, yeah, connections have been made. Yeah, that's the indicator, remember. Okay, it has started charging. Well, the generator here, as you can see, is connected to the drill machine and to the transformer and to my night bulb. Okay.